All right, how are we doing again today? Just checking in here. Yesterday, you should have gotten the intro to physics or forces notes, talking about Newton's second law. You should have gotten your mass lab and been able to measure the mass of a couple different pieces of equipment on our mass balances or our triple beam balances. From there, you had to calculate the weight on Earth and the weight on the moon, and we should be good to go with that lab. And a little bit of reading last night, so hopefully you did it. Today our primary focus is to look at free body diagrams or force diagrams. You already did a little bit of homework tonight, 2 worksheets, one primarily focusing on force diagrams, and both of them primarily focusing on force diagrams. Can you draw them? Do you know what's going on? Because they're going to be utterly key from here on out. Every single problem you do from here on out, I will expect that you do the force diagram before you do the calculations to make sure you're not missing any of these extremely crucial pieces. So, I hope you're giving yourself the utmost respect. Excited to be the figmented voice coming through the wall. I mean, it's got to be good to listen to my beautiful serenading voice without seeing my ugly mashed up face. Hopefully you didn't agree to that, but hey, I'm not here, so it doesn't hurt my feelings. Here we go. Here's your question of the day. It says, what is an astronaut's weight on Earth if he weighs 2,464 newtons on Jupiter? The acceleration due to gravity on Jupiter is 25.94 meters per second squared. I'm going to ask the sub to go ahead and stop the recording here and give you work time. Go. All right, I hope you got a chance to work that through. If not, you probably were paying attention. We should be able to work on answering this question so far based on the key things we talked about yesterday, the differences between weight and mass, because weight is the force of gravity on your body, and mass is the stuff, the matter that makes up your body. So here we go. I'm going to walk you through the board here. It says, what is the astronauts' weight on Earth if they weigh 2,464 newtons on Jupiter? What is the astronaut's weight on Earth? That's what I'm looking for. Weight on Earth. Key thing it says here, the acceleration due to gravity on Jupiter is 25.94 meters per second squared. So here's what I'm going to do. I'm going to draw what I know. I look in here, it says, well, it's asking me for what is the weight on Earth, which I also know is my force on Earth, if you want to write it that way. That is what I am looking for. What does it tell me? What tells me my weight on Jupiter, also known as my force on Jupiter, right, is 2,464 newtons. It tells me then my acceleration, the acceleration on Jupiter is 25.94 meters per second squared, and oh, it doesn't tell me my mass. Okay, so we don't know the mass. We're trying to think, well, what do I need? I know it's weight on Jupiter, which means I have a force and I have an acceleration. I need a mass. Well, something we learned yesterday is that weight is the force of gravity on your body. Therefore, your weight on Jupiter, because it's a bigger planet, should be more than your weight on Earth. However, I know that the stuff that makes up you, the matter that's actually in there, does not care if you're on Earth or on Jupiter or on a star, because the stuff is not going to change. Gravity changed. So what I need to make sure I do is, in order to answer the question of my weight on Earth or my force on Earth, well, I need a couple of things. To know force, I need to know a mass on Earth. I also need to know an acceleration on Earth, which hopefully you know the acceleration on Earth is 9.8 meters per second squared. My mass on Earth, what kind of a cool thing is that is the linking piece between these two problems. Why? Because your mass doesn't change. The stuff doesn't change based on where you're at. What does change is gravity's force on it. Okay? So that's where we have to start. We have to solve for my mass in order to figure out my weight on Earth. So I'd ask myself, well, do I have an equation with force, acceleration, and mass in it? Hopefully the answer is yes. I know that F equals ma. Force equals mass times acceleration. And we said yesterday that if you were looking for the force of gravity, we could call that the weight. Because if you know the mass, which we will get to, and we know the acceleration of gravity, in this case it's on Jupiter, it's the same equation. Because force and weight are the same thing. So let's solve for that. So I know, if I look at that, it's a plug-and-chug problem again. I know that my force is a mass times an acceleration. Well, I want my mass all by itself. So I'm going to divide by my acceleration. And I am left with force divided by acceleration equals my mass. Well, if I look here, do I know my force? Yup, on Jupiter I do. Do I know my acceleration on Jupiter? Yup, I do. Therefore, I can find my mass, which doesn't care if I'm on Jupiter. So let's do that. It's a plug-and-chug problem. 2,464 newtons divided by 25.94 meters per second squared equals, well, if I do that out on my calculator, I should get 94.68 kilograms. Remember, kilograms must be the mass unit we're working with. Why? Well, if I only look at my units, what is a Newton? A Newton is a kilogram times a meter per second squared. Divide on the bottom between a meter per second squared. They go away. The only thing I have left is kilograms, and sweet! That's what I wanted. Okay? So now I know my mass. My mass is 94.68 kilograms. Once again, why is that the linking piece? Because the Earth and Jupiter do not care where I am. The stuff in my body is not going to change. So now we can finish this problem. And if I rewrite what I know to make it look cleaner here for you, I know that I'm looking for my weight on Earth, which could also be the force of gravity on me on Earth. That's what I'm looking for. I know my mass is 94.68 kilograms, and I know my acceleration here on Earth is 9.8 meters per second squared. Do I have an equation with those three variables in it? You better believe it, I already used it. Why can we still use that? Because this is now the force of gravity on Earth and the acceleration on Earth. So you could write weight of gravity on Earth is your mass times the acceleration of gravity on Earth is a little g. Okay? You can see how it is. They are, once again, essentially the exact same equation. So let's plug in what we know. It's, once again, a plug and chug. I know my mass, I know my acceleration. Force equals 94.68 kilograms times by 9.8 meters per second squared. If we do that on my sweet little calculator, I'm going to get 927.864-ish newtons. Okay? Now to end this problem, notice how I haven't rounded yet. To end this problem, I need to look up and say, well, how many sig figs was I given? I was given 1, 2, 3, 4. I was given 1, 2, 3, 4. So my answer could have 4 sig figs. So if I do that, that's 1, 2, 3, 4. So that 6 is going to round it up. It should be 927.9 newtons is how much I weigh on Earth, or this individual weighs, the astronaut weighs on Earth, 927.9 newtons. So, challenging problem? I think the challenging piece is to come back and figure out that your linking member is your mass, because your mass doesn't matter where you're at. It's the stuff that's in your system. Once you have that, you basically use the same equation twice, because it's the equation that works. It's the only equation we have for that. All right? Hopefully that helps walk through a couple of practice problems there. Hope that helps make sense. We'll continue to do more problems like this. So to pick up where we left off yesterday, we need to go back to force diagrams. It's a skill that you need to use, a skill that you must know, a skill that you must master, because drawing your picture becomes half the battle on some of these problems. If you draw everything correctly, it turns into a plug and chug majority of the time. If we forget stuff in our pictures, we typically forget stuff in our calculations, and we get the wrong answer. So, what is a force diagram? Once again, the book will call them free body diagrams or force diagrams, either one. If you were to define it on your textbook, it is a picture, which is a model that represents the forces acting on the system. Now, what you need to look for right here is it says all the forces acting on the system, which is super, super, super important. Not some of them, not a part of them, but all of them. Your picture should be all-encompassing of what is happening in the problem. Because if you forget any of them, it's going to mess up your answer. So, once again, let's just say I like to start making everything into a box. Because then for me, I can clearly see my vertical lines, and I can clearly see my horizontal lines if I need to. But I make everything into a box. Now we talked about this yesterday, that your arrow, a force diagram is going to tell you where the forces are coming from. They can be drawn as a pole, right? It has the arrow, which talks about the length of the arrow, tells you the size of the force. And the directional piece tells you the direction of the force. So I can create a push as well. I can have a push, this pushing the box. Notice how my length of my arrow is much smaller, so I'm going to have a smaller force. My directional piece is pushing on the back of it, so it's still going in that direction. It is just showing it's a push, whereas this is showing it's a pull. Clearly, we can do them vertically as well. We can have something pushing down on the object. We can have something pushing up on your object. Okay? Reminder though, it's just the length of the arrow tells you the size of the force, and the direction tells you the direction that the force is acting. Okay? That's going to become basically your basics every single time. How long should my arrow be? In what direction should it point? Cool. We should be asking ourselves. Now, to do this correctly, we got to learn about a couple forces that maybe you haven't heard of before. One of these forces is called the normal force. There's a couple of key things to know about the normal force. One, it is a contact force, which means an object must be touching another object to have contact. Therefore, you can actually have this force. If things are not touching, you do not have a force. So if I just drew a box that is floating out in outer space here, there is no contact with anything. There is no normal force. However, as soon as it's in contact, let me draw my beautiful ground here, and now I put that same box on the ground. We now see that that box is in contact with the ground. It is a contact force. Now, where is that force then? Well, the direction is always perpendicular to the surface. So what does that mean? That means in this picture, well, here is my contact, therefore it is perpendicular to the surface. Normal force. Once again, the length of the arrow tells you its size. The direction tells you where it's going. It is perpendicular to my contact surface. And it's denoted as F of n, meaning the normal force. Okay? Often, this is a force that keeps things from falling through the ground or through the earth or through a material. But we need to know it is not a reaction to gravity. Why? Well, because in some problems, you can have something that is, your box is right here, and maybe it's sliding down a vertical wall. If it's sliding down a vertical wall, clearly here is my contact, therefore my normal force goes here. If it's sliding down a vertical wall, we should clearly know that gravity is affecting it downward. So here we can see it is not the reaction to gravity. It is a contact force. It is always perpendicular to the surface that it's in contact with. We'll talk through how to think through the size of this force, but those are the main components you need to do. Okay? So it is always a contact force. It is always perpendicular to the surface. It is not a reaction to gravity. It is denoted as F of n. Okay? Normal force. Another force you need to know, which hopefully you do by this point in time in your life, is the frictional force. Once again, you should know friction is a contact force. If two things are not touching, there is no friction between them. If they are touching, there is friction. It is demanded, again, a contact force. How this one looks different, though, than the normal force is because this one, if that is my beautiful boxed object, and here's the surface it is in contact with, we see that it is always opposes motion and is parallel to the surface. So let's just say my object has a velocity going this direction. Okay? If it opposes motion, that means my frictional force must be in the opposite direction, and it's parallel to the surface, whereas my normal force was perpendicular to the surface. So frictional force, you need to know it opposes motion. It's the opposite of the direction going, and it's parallel to the surface. It must have contact to have this component. We're not going to talk too much about static and stationary or kinetic. We'll get there later. But the key thing to remember, if there's no contact, there's no frictional force. If there is contact, it always opposes where it's actually going. So frictional force. Last but not least, that we're going to talk about before we do a couple practice problems here is tension. Tension basically is a force that's in a cable, a rope, or a string. The book's going to say tension. They might tell you the force in the string is, or they might say the tension in the string. So force in the string. You might also see them write tension. Or the book might also write the force of tension. Kind of depends on what chapter you're reading through or how the problem's laid out. But we should know that what tension is, it is just the force in the string. And for the sake of this class and for your math level, there's some key things we clarify. One, we assume the force is equal throughout the entire string. Clearly, I know that that might not always be the case in real life, but for the sake of this class, the force is equal throughout the entire string. And the string's assumed to be massless, which once again I know doesn't exist. There's no such thing as a massless string, but unless you plan on doing it calc-based, we cannot do that problem, so we assume the string is massless. So tension is just the force in the string. Not a big deal. But some keywords. So let's do a couple practice problems here. Here we go. We're going to do a couple together, then I'm going to let you do a couple, and then I'm going to end with a problem. You're going to do the picture two and then calculate, and then we'll be done for the day, and you'll be able to get some work time here. So it says, draw the force diagram for a book sitting on the edge of a table. So what am I going to do? I'm going to first draw the legit picture. So here is my really sweet drawing of a table. Okay? And I have a box that is sitting on the edge of that table. I typically always draw the scenario of the problem, which is big picture, and then I zoom in on what is happening to draw my force diagram. Okay? So I now have a zoomed in picture. So I have my table. I have a box sitting on my table. So what are all the forces affecting this box that is sitting on the table? Well, I know that gravity affects everything. I know that gravity is going to pull it towards the ground. So I'm going to say force of gravity is affecting it downward. Well, I also know that if you look carefully at this picture, that right here there is contact. So there's a contact force, which means there must be a normal force, the opposite direction, perpendicular to the surface. So there is a normal force that is perpendicular to the surface. Now what I want to do is think carefully here. My box that is sitting there on the table. My box is not hovering into outer space. My box is not falling through the table. So what that's really telling me is my length of my arrow for my normal force must match the length of my arrow for my gravitational force, because neither of those two are winning. So let's say my normal force is 10 newtons. My force of gravity would be negative 10 newtons. They're affecting each other in opposite directions, but the key thing to know is they are the exact same size arrows. Why? Because the book isn't falling through the table, and the book isn't hovering into outer space. Clearly, it's sitting still. Why does that become important? Well, because if I was to add up my forces in the y direction, I would get, well, a positive 10 newtons plus a negative 10 newtons. If I add those up, I get 0 newtons as my total, which tells me that my mass times an acceleration must be 0. Why is that important? Well, it's impossible to have a 0 mass, which must mean that my acceleration equals 0, which means nothing is changing. Well, if my box is sitting still, nothing better be changing. It doesn't have a position change. It doesn't have a velocity change. It's doing nothing, and my picture just showed me that. So that's how I think through these problems. So I might not do all the calculation pieces to it, but let's think through this one here. It says, draw the force diagram for a book being pushed across the surface of the table. Once again, I start off by drawing the big picture scenario. Here's my table. Here is my box. It is going this direction with the velocity, right? It's being pushed across the table. So now let's zoom in. Here's my table. Here is my box. So this would be my force diagram. So what's affecting my box? Well, a couple things I see again. Gravity is going to push it down. Now, is my box hovering into outer space? No. Is my box falling through the floor? No. Is there contact between the box and the floor? Yes. Therefore, because there's contact here, we must have a normal force. And that normal force should be the same length arrow as my gravitational force. Why? It's not hovering in outer space and it's not falling through the floor. So that looks like my y direction. Now my x direction, so it's being pushed across the table. Therefore, let's make a push. So I'm going to draw an arrow from the back side to make a push. Being pushed across the table. So I'm going to call it force of P, force of push. Okay? So it's going across the table to my right. Awesome. But if there's a contact surface, there's another force that comes into play. The one that opposes motion. What force is that? Oh, Mr. Hill is calling me. It's the frictional force. You are right. It is the frictional force. The frictional force opposes motion, so it goes in the opposite direction. And if the object is moving, it must be less than the push force because it's moving to the right. And I'll call that the F of F, so frictional force. And now we have a diagram that shows everything that's happening. We can clearly see in this diagram that gravity is affecting it. There's a contact, so there's a normal force. I know that it's being pushed by someone, and if it's sliding, there's always a force with the contact that opposes it, friction. Most problems will start to give you those numbers, and now it turns into plugs and chug problems. But if we don't draw a picture, we're going to forget one of those problems. Let's try again. Okay. Draw a force diagram for a monkey hanging on a rope from a tree limb. I want you to do this right now. Go. So feel free to stop the program for a second here. Give them 30 seconds to think, and then resume. Awesome. I hope you had time to work. I'm going to draw it out. Once again, remember, I draw a big picture. So here's my tree coming down. We have a tree limb sticking out. Cool. We have a string that has a monkey attached to it. Right? Remember, I draw boxes. I'm not going to draw a monkey. I'm a horrible drawer. I'm going to draw the box. So my box is the monkey. So now we zoom in. I have a monkey that's hanging from a string. So, well, what are the forces affecting this? Well, clearly, if it's hanging from a string, there must be the force in the string, which we call tension, right? F of T, the force in the string. What else is affecting it? What else is always affecting? I hope that answer comes to be gravity. We know that gravity is going to affect it downward. Now, if I'm thinking here, the monkey is hanging, therefore it is stationary. It's not swinging, it's not climbing the rope, it's not falling to the earth. It is stationary, which must mean the length of this force of tension arrow must equal the length of my force of gravity arrow, because my total forces in that y direction need to be 0 if nothing's happening. So my total force in the y direction of force of tension plus, we'll call downwards negative for this problem, my negative force of gravity, we should get 0, which means my tension force must be equal and opposite to my gravitation force. Are they? Yeah. Why? Because he's not falling to the earth. He's not climbing up into the air. They're equal and opposite on this case. There's nothing else affecting it. It's not swinging side to side, so there's no friction. It's not touching another object, so there's no normal force. It's just the tension in the string and gravity. So let's complicate this problem a little bit. It's more fun. So let's draw a force diagram for a monkey hanging from 2 ropes attached to a tree limb. Go. Awesome. I hope you have time to think it through and time to talk to the person next to you and match it. And if not, you can stop the recording here so you can. But I'm going to start drawing. Okay? We have, once again, my beautiful, beautiful tree with a really cool limb sticking out of it. We now have 2 strings that are going down to my monkey. Once again, it's a box, a really ugly box this time, but a box. So I'm going to zoom in now because that's my overall picture. Let's look at what's really taking place. So I have my monkey, which is my black box. Okay? I know it is hanging from 2 strings. And I know that if it's hanging from 2 strings, that it's going to be equally balanced. Otherwise, it's going to tip and swing one direction or the other. Which must mean that the force and tension in string 1 and the force of tension in string 2 must be the same as each other. Therefore, it has to be the same length arrow. Cool. Well, what else is affecting this? I hope somewhere in the back of your brain that's creeping in and saying, gravity's affecting it. Gravity, Charles, gravity. I know you can't see my hand, but it's gravity. You're correct. Gravity is affecting it. In what direction is gravity affected in? I hope we're all saying downwards towards the earth. Okay? So I know that the force of gravity is going to be affecting it downward. Well, how much? Twice as much as the force of tension. Why, you might ask? Well, let's say, for example, my force of gravity ends up being 10 newtons. Let's say negative 10, because we'll call down negative, up positive. Well, we know that then this top string here must be 5 newtons, and this other string must be 5 newtons. Why? Because 2 strings are equaling 1 downward force. You can add them up. If we get to that point, force in the y direction is going to be force of tension in the first string plus force of tension in the second string plus a negative force of gravity. That really means the total force in the y direction is 2 times the force of tension in string plus negative force of gravity. Well, the monkey's not going anywhere, so the total force has to equal 0. So 0 must equal 2 times the force of the tension plus negative force of gravity. If you were to bring this over to the side, you get force of gravity equals 2 times the force, the tension in one of the strings. Did we do that? Yeah. There's 10 newtons here, 5 newtons here, 5 newtons there. 5 plus 5 is 10, making it equal and opposite each other. All from the picture that you drew. And then we added some numbers to think conceptually around it. Okay? That's what your homework's going to require of you. It's to draw the pictures. It's to then draw the arrows for the forces that are on there, labeling all of the forces, and then start thinking through, mathematically, what is that telling me now? Now I know where my arrows are going. I know how big those forces are and what direction they're going. So what's happening in the y direction? What's happening in the x direction? They're 2 separate pieces. Last one I want you to do and read through. I'm going to give you time to read this. I'm not going to work this one out today. You'll see it done tomorrow. But here is your question to think through. Answer, go on to your worksheets. Tomorrow, I will be doing this question on the board anyways. So please give yourself the utmost respect. You should have 2 worksheets you're getting tonight. There's a couple of readings out of a book and some practice problems. Once again, it comes down to, can you draw the picture? If you can, we'll see the math turn into a plug and chug. Please give yourself that much respect. I will see you guys shortly, someday, maybe. Maybe I'm watching now and you just can't see me.